because you guys tend to be really good at science. So let's get that done. Hold on to your question. So like I see like Alexis, Tanjiro, you guys have questions, so just hold on, and Reborn, so just hold on to those. You three, I'll call on first after class is over. But for now, let's go ahead and get this going. Dun, 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 dun. All right, we did temperature change, so now we're on. How are temperature and mass related to thermal energy? Dun, dun, dun. Dun, dun, dun. All right, so first, let's just go based on what we think we know. Let's see if we can do this first one. Two eggs are identical except for their temperatures. One is the hot egg, one is the cold egg. Which has less thermal energy? Thermal energy. Alexis.
Why didn't I raise my hand? Oh, it's still up?
Yeah.
Why didn't I raise my hand?
Okay, well now I know that. Okay. Hinata.
The hot egg.
The hot egg has less thermal energy?
Wait, never mind. I meant the cold egg.
The cold egg has less thermal energy. Yes. So guys, the cold egg has less thermal energy because again, if you put a thermometer in the cold egg, it'll be cold or whatever. But if you put the thermometer in the hot egg, it has thermal energy, heat. It's giving off a special energy. And fun fact,
it's heat.
Whoa.
Has a lot of energy.
Make sure we're on mute. Make sure we're on mute, everyone. Heat does give off energy. Heat can actually heat things up and give things energy. I'm trying to think of a good example other than like an oven, but most things like you can't really use cold as energy. Nothing gets energy from being cold, but things can get energy from being hot. Okay, like a stove. This is really the only example I can think of like just right now. But if you think of like a solar panel, light energy, that is light, that is heat giving energy and then helping with electricity. But again, cold doesn't really give any electricity. So thermal energy, heat, remember that. Okay. Two meatballs are identical except for thermal energy. Which meatball has a higher temperature? Ooh, the meatball with more thermal energy or the meatball with less thermal energy? Dun, dun, dun. Kabir.
The meatball with more thermal energy.
Yes. Oh, yes, the meatball with more. The meatball with more thermal energy is going to be hotter. All right, boom. Two 9-kilogram blocks of concrete are identical except temperature. Which block has more thermal energy? The hot block or the cold block? Stella.
The hotter block of concrete.
The hotter block. Yes, that's going to have more energy. All right. Two tennis balls are the same except their energy. Which tennis ball has a higher temperature? Tennis ball with more thermal energy or the tennis ball with less thermal energy? Agni.
The tennis ball with the more thermal energy?
Yes. Yes, yes, yes. All right. Two bowls of oatmeal are identical except their temperature. Which bowl of oatmeal has less thermal energy? Less thermal energy. Reborn.
Colder bowl.
Sorry. Yes, the colder bowl. Good. All right, we got next one. Okay. Which object has the least thermal energy? They're all an egg, but which one has the least thermal energy? Tanjiro. or not? All right, Tanjiro, you're taking too long. I'm going to someone else. Okay, Alexis.
The egg at a temperature of 79.
Yes, that has the least thermal energy because it's the coldest. There we go. All right. All the liquid is the same. It's all paint. Okay, which one has the most thermal energy? Ooh, this is interesting. This one's interesting, guys. Pay close attention. Okay. Which one has the most thermal energy? They are all at 0 degrees. Okay, so far they're all at 0 degrees. The only thing that's different is how much of them there are. So which one has the most thermal energy? So that's interesting to me. Okay, which one do you think it is? Anwar. Oh, he's typing 112. All right, let's find out. So let's find out why, because guys, they're all the same temperature. It says 128 ounces. Okay. So, dun 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 dun. All 4 volumes of paint were the same temperature. The liquids are the exact same. So the largest volume will have the most mass. Since 128 had the most mass, it will have the most thermal energy. So if you have basically a tiny blanket and a big blanket, and they're both 60-degree blankets, which one do you think will keep you warmer, the tiny blanket or the big one? Well, probably the big one, yeah. You know, because you could put that all over your body. The little one, even if it's as hot as the big one, it's not going to keep all of you warm. It'll keep like your foot warm, but that's about it, you know? So that's why. All right, next one. Okay, the least amount of thermal energy. Again, this one, they're all the same temperature. So which one has the least amount of thermal energy, even though they're all the same temperature? All right, Filmon.
So which one has the least?
Yes.
Okay. Wait, they're all the same though.
They are. So based on what we just learned though, and I use my example of a small blanket and a big blanket, which one of these has the smallest amount of energy?
The second one?
The second one, yes. Because again, if we use the blanket as an example, if my tiny blanket and my big blanket are both very warm, they just got out of the dryer and they're warming me up on a nice winter day, the small blanket is probably only going to keep my hands or my toes warm, but the big blanket's going to keep all of me warm. So out of those two, the one with the least amount of energy would be the little blanket, just like in this case. The one with the least amount of energy is the 75 milliliters of water, all right? Because that's only like a little bit of water versus a lot, okay? So, good job. Okie dokie. This one, which one has the least amount of thermal energy? Right? The least amount of thermal energy. There are 1, 2, 3, 4. There are 4 people I still have not heard from. I would love to hear from one. Oh, Pooja.
I think the last one.
Okay, you think the last one? So I'll give you a hint. The last one has the most thermal energy. So that's the highest one. We want the smallest one because it says least. So if this
The
one's the
first,
highest one, what's the
first
largest?
one.
Yeah, the first one. Good job. Good job. All right. Now this one, we want the one with the most energy. We want a lot of energy. Okay. Close attention, though, that they're all the same temperature again. So what do we do, Portia?
Sorry, I'm trying to read these real quick.
You're fine.
Wouldn't it be the top one that's right?
Yes, it would be. Good job, Portia. Yeah, because that was the most amount of water. If you have a little bit of hot water, you might, if you drink it, you'll get like a little tongue burn or something. But if you drink a whole glass of hot water, man, your whole throat's gonna be burning. You know what I mean? So that one, yeah, definitely would have had the most. Okay. This one wants to know the least amount of thermal energy. Least amount. Lalita.
Second.
You're close. You're close.
First.
Nope, you're closer with this one.
Third.
Yes. Yes, it would be the third one because that's the smallest. So this word right here, least, that means small. That means super small. So since 8 is the smallest number, that's why it's that one. All right, how many left do we have? This is our last one, and we have one person who hasn't done anything yet. So I would like for that person to answer this. Okay, so I'm gonna go over to that person. Okay, I can see. So this one wants the least amount of thermal energy. My last person. Hopefully you know who you are.
Is it me?
No, I've called on Tanjiro over. Well, I technically called on you. I just didn't hear from you yet. But because your mic wasn't working. But I would love to hear from Demaya. Because I haven't heard anything from her. And I just want to make sure she's not napping. Or make sure she's awake. So I can mark her present. Demaya, are you asleep? Wake up. Yeah, I guess she's asleep. Okay. Demaya, I'm going to mark you absent. Better wake up, hopefully. Okay, well then in that case.
I'm not asleep. I'm eating.
Oh, well then I still need you to answer this though.
Which have its least thermometer?
Yeah, least. So which one's the smallest?
It says
Look at him.
Thermometer.
I don't know.
So look at the number, look at these first numbers.
8.
Yes, see, you knew. Don't doubt yourself, you knew. Good. Oh, is this like a bonus stage? Oh, I guess it's not. This is part of the class. Okay, I thought this would be like bonus. Well, then, technically, Akri and Tanjiro should be next, and then that means the last two can be up for anybody. So, let's see if we can get all these right. A pile of gravel, so just like rocks, pile of gravel is 47 degrees. So this is pretty cold. So they're cold rocks. Then it is combined with another pile of gravel at the same temperature. All right, select the better estimate for the temperature of the large pile of gravel. Select the better estimate for the temperature of the large pile of gravel. Dun, dun, dun. Tanjiro.
47 Fahrenheit.
Yes, because if you remember, because it specifically said another pile of gravel at the same temperature. Same temperature. It's a bigger pile, but it's the same temperature. So yeah, good job. Okay, blueberry muffin, yum, is at a temperature of 38 degrees Celsius. Then the muffin's thermal energy decreases, so it cools down. Assume its mass doesn't change, so it doesn't get bigger or smaller. Which is possible, or which is a possible new temperature for the muffin? Dun dun dun. So, Akrit, you're the last one I haven't heard, or sorry, Naruto, you're the last one I haven't heard from. So based on this muffin at 38 degrees, that's gonna get a little bit colder because it's cooling off. What's its new temperature? Say anything?
Asking me,
Yes.
I'm gonna start like thinking of the difference of the cold and the heat, so I can know what the different temperature is for it.
Sure.
Like you said, it's supposed to be hotter, right?
So right
supposed to
now
be
the muffin is at 38 degrees, and it's telling us that we're letting the muffin cool down. So which temperature would be cooled down from 38?
32.
Yes, good job. All right. Okey doke. Everyone has participated at least once, if I'm not mistaken. So then it is open up to everyone now. All right. So we have a 200 milliliter, or sorry, 2000 milliliter bucket. Keep in mind it says milliliter. 2000 sounds like a lot, but it's milliliters, so it's actually not a lot. Of paint is a temperature at 52 degrees. The paint is divided equally into 4 smaller buckets. Each bucket is at 52 degrees before the paint is poured. Select the better estimate for the temperature of each smaller bucket of paint. For the smaller buckets. Hinata.
75.
You said, wait, did you say 52 or 75?
75.
75? Okay, I'll let you know it is not 75. Okay,
52 then? I got it wrong then.
that's okay. So just remember, each bucket is at 52 degrees, just like the big one is at 52 degrees. So when you pour the paint inside of it, it's not gonna change temperature, so it'll stay 52. All right. Now, there's a 55-ounce rock, so it's kind of heavy rock, kinda, at 74 degrees. Then the rock's energy increases, I'm assuming because of the sun. Assume the mass doesn't change, so the rock doesn't get bigger or smaller. So what's its possible new temperature? What is its possible new temperature, Billmon?
82.
82, yes, because it says its energy increases, so this rock's getting hotter. Good. All right, 2-pound bucket of sand, temperature at 14 degrees, so that is some cold sand. Then it's combined with another 2-pound bucket of sand at the same temperature. Select the estimate for the temperature of the large bucket of sand. All right, so we combine the sand, same temperature. So what temperature is it now, Portia?
I forgot to put my hand down.
Oh, that's okay. So Stella.
Yeah.
Is your hand is up? Did you want to answer?
My. Oh, that was an accident.
Oh, okay, that's okay. So Philmon. Is anybody else's hand up on accident? Make sure your hands are up if you want to answer. Philmon, do you want to answer? Can't tell.
Yes.
Okay, so what's the answer? I couldn't hear you.
Oh, I was talking on mute.
Yeah.
That happens to me so much these days.
Telephone.
So is it getting hotter or colder?
So it says right here, same temperature.
How do you call
Oh, 14.
14, yes, good job. Is that Mickey?
Yeah, he's up here annoying me. You wanna say hi?
Mickey.
Who's that?
Hi, Mickey.
What?
What?
Hi.
Hi. How are
Okay, no more. Now I'm in class. I'm in class. Go. That's it.
Right here again.
That's it.
Bye, Mickey. All right, wow. Oh, Kabir was right. He said that there's 4 stages. Turns out today's lesson is a long one. Who would have thought? Okay, well, today's still going, and I don't think it's called bonus, is it? No, it's not a bonus round, so we're still going, guys. All right, here we go. A 24-ounce pile of peanuts is at the same temperature of 67 degrees, so just like, normal temperature. Then the peanuts are divided in half. The amount of thermal energy in each part is about blank the amount of thermal energy in the original pile. So the energy, the temperature, the thermal energy is about what? The same, twice as much, or half as much? Naruto. Okay, Naruto, I literally called on you. Said I want to answer. Come on.
Oh. The
Okay, I'm gonna call on someone else. I don't hear anything. So, Alexis.
Amount of energy since each part is about is it I don't know what it means though. It says
That's okay. Here, let me show you. Let me show you guys. So, if we have a pile right here, okay, and it's 67 degrees, okay, all they did was split the pile in half. So, now we have a pile over here and a pile over here. So now it wants to know what the energy is. So your options are the energy, so the temperature of the peanuts stays 67. So does it stay 67? Does me splitting the peanuts make it hotter? And it says twice. So does it make it 134 degrees? Or does splitting it make it colder and turn it into 33.5 degrees?
wouldn't it make it split?
You think so? If I split the pile, the temperature changes?
I don't know.
So
No,
let's
it stays the same.
exactly. Yes, it stays the same. That is correct. So that goes for everybody. So guys, it's trying to trick you. It's literally trying to trick you. Think of it like this. If I have a birthday cake, I'm gonna try and draw one. Okay, if I have a birthday cake, here's my little candle, my little fire. Okay, happy birthday, blah, 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 whatever. Okay, I have a piece of cake. Let's say my cake is at 67 degrees, which would never happen. Cake should not be that hot. And then I cut out a slice. Boop, 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 boop. So now I have a slice of cake. Okay. Does my cake change temperature all of a sudden?
No.
No. My slice doesn't change temperature. My cake's still the same temperature. The cake got smaller, but the temperature doesn't change. So that stayed the same. All right. Boom.
Oh, now I
Again.
know.
Yeah. So guys, these questions, some of them are trying to, what? The amount of thermal energy in each part is about 1/2. What the heck? That's wrong. This is dumb.
That's wrong.
When matter is divided into parts, the total thermal energy is divided among the parts. So 12 ounces will have half as much energy and 24 ounces. That's wrong. I don't like that answer. Hold on.
The website got it.
That's wrong. You told me it was right.
Mr. Hughes is going to answer this next one because that doesn't make any sense. Okay, hold on. 3 glasses of milk have the same mass and temperature. They're combined in one large bowl. Large bowl starts at the same temperature. Temperature of the large bowl is about the same as temperature of the 3 glasses. The same. You took 3 glasses of milk that are the same and put them in a big glass, which makes them the same. So how come that's right, but the other one was wrong? See, that's what I don't get. That was, no. Okay, the amount of energy, 4 cups of hot chocolate have the same mass temperature. They're combined into one large pot, same temperature, large pot, blah, blah, blah. So I poured 4 cups of hot chocolate into a pot. Now I have a big bowl of hot chocolate. So the thermal energy is the freaking same. How is that wrong? It was just right. When matter is combined, the thermal energy of all the parts is also combined. So the larger pot of hot chocolate will have 4 times as much energy as the small cup of hot chocolate. Interesting. So I guess, what it's saying, I guess, in my opinion, is I'm going to use my blanket again. So if I have a tiny blanket, if I have 4 tiny blankets that are all hot, you know, I can cover my feet with this one. Gross. I can cover my hands. Yikes, that's so bad. Ooh. Cover my hands. I can cover, I don't know, my face. And then I can cover my, I don't know, my ear. I don't know. Let's say something like that. Okay. So, but then I turn it into just one gigantic big blanket. That's hot now. And so now I can cover, I guess, all of me. I guess that makes sense. That's confusing. Because the last question we just talked about literally said something very similar. Am I wrong? Didn't it say we combine 4 things into one big thing and it stayed the same, but this time we combined 4 things into one big thing and it is 4 times hotter. So I don't know. That doesn't make sense. Okay. Mr. Hughes is going to keep going because if I don't know it, then how do I expect you guys to know it? An apple is cut into 2 pieces. The temperature of each piece of apple is the same. Oh, look at that. Okay, so hold on. So that's a temperature. A pile of nails is at a temperature of 30, divided in 4. The amount of thermal energy in each part is about blank. The nails are divided. The nails is at a temperature of 30. The nails are divided into 4 parts. So the energy is 1/4. Okay, so there is a difference between temperature and thermal energy. Hold on, let's see if I get this. 3 balls of pizza dough have the same mass and temperature. They're combined into one larger ball. The temperature of the larger ball is the same. Okay, good. So temperature and thermal energy, we need to be really careful. Even Mr. Hughes does. So when it's talking about does the temperature change, it's usually no, because if I have 2 ice cubes together, they're still the same temperature. But I guess as far as thermal energy is concerned, their thermal energy changes. Okay, so let's try this one. 3 bowls of soup have the same mass and temperature. They're combined into 1 large bowl. So now it's a large bowl of soup. Temperature. The temperature of the large bowl of soup is the same, right? Yes. Okay, see now this one says thermal energy. Okay. So if it's temperature, okay, I think I get it now. A 200 milliliter bottle of apple juice is at a temperature of 60 degrees. Then the apple juice is equally divided into 2 smaller glasses. Each glass is 60 degrees. The amount of thermal energy in each part is about, so if it was divided in its energy, now it's 1/2. Haha, okay, so Mr. Hughes got it now. Okay guys, so class, boom. I apologize. So I guess when it comes down to it, make sure you're paying attention to whether it says thermal energy or temperature. Because like with cake, if you cut a piece of cake off of the normal cake, the temperature is not all of a sudden going to change. But the thermal energy, I guess, would, because you're taking something big and then taking a small part of it away, which takes away some of the energy, but not the temperature. So this one talks about 4 bottles of water that are combined into a large pitcher. The thermal energy in the large pitcher is now what? So since it wants thermal energy, and we just made 4 bottles become 1 big pitcher, what would it be? Does anybody think they know this time around? After all of that explanation? Hinata?
1/4?
Could you say 4 times?
I said 1/4, I think.
So read it carefully again. It's 4 bottles being combined into 1.
Oh, it's 4 times.
So it's 4 times. So if we see the word combine in thermal energy, it's going to be times. If we see the word divided in thermal energy, it's going to be a fraction, which makes sense now that you think about it, because if it's combining, that becomes 4 times. If you're dividing, you're dividing. So that's a division, a fraction. And then if it's temperature, I'm assuming it's just temperature equals the same. So good thing we're recording this and putting it on YouTube so you can rewind this and, if you need help with that. Got it. So combine equals times, divide equals fraction. Interesting. All right, well, we're done. Mr. Hughes learned a lot today, so that's always fun. I'm gonna stop recording.